The neuron's outer shell, known as the neuronal membrane, plays a crucial role. This phospholipid bilayer acts like a guardian, determining what stays in and what goes out. Embedded within it are proteins that form channels, like guarded gates, that allow specific ions passage in and out of the neuron. Now imagine a neuron at rest. It maintains a voltage of -70 millivolts, known as the resting membrane potential. Two forces govern this exchange of ions: diffusion and electrostatic pressure. But how does this resting neuron spring into action? The answer lies in a phenomenon known as an action potential. Picture a switch flipping on, and suddenly, sodium ions rush into the neuron through channels open just for them. This influx of sodium ions, driven by their higher concentration outside the neuron, causes the membrane to depolarize. As the voltage changes, the sodium channels close and the potassium channels open. Like sodium, potassium also obeys the laws of concentration, flowing out of the neuron, leading to the neuron's repolarization. Following this, there's a period of hyperpolarization, where the membrane voltage dips even lower than the resting potential. But don't worry, the balance is restored, thanks to the sodium-potassium pumps that replenish the original sodium and potassium concentrations. This entire process is governed by the all-or-none law, stating that every action potential, once triggered, is of equal intensity. Now, these channels that we've been talking about can be opened in various ways. They could be stretch-activated, voltage-gated, or even neurotransmitter-gated. As the axon terminals depolarize, voltage-gated calcium channels open, leading to the release of neurotransmitters. These neurotransmitters then bind to receptors on the postsynaptic neuron, continuing the chain of communication. Interestingly, action potentials can only move from the soma to the axon terminals, a process known as orthodromic conduction. The speed of these nerve impulses is boosted by myelin, a fatty tissue produced by cells in our nervous system. This leads to a method of conduction known as saltatory conduction. To summarize, neuronal communication is a complex process involving voltage changes, ion movement, and chemical exchanges. It starts with the resting membrane potential, moves through depolarization and repolarization, and ends with the release of neurotransmitters. All of this happens in milliseconds, seamlessly ensuring that our brain and body function in harmony. In the grand scheme of things, we are but a beautiful orchestra of neurons, playing the symphony of life. Don't forget to subscribe to the channel.